think I'm live. You just open up Twitter, or I guess it's x.com. I want to see if this thing actually, I can't type today, actually shows up as me broadcasting. So I think you have to be signed in for it to show up as live. Puts like a little circle around it. Let's say, hey, on x.com, when I broadcast live, doesn't show up to people who are not logged in. Is that required? And then I'll test it over on my other computer here with a logged in user. I got a blue check mark. Pay $4, you get a blue check mark. Where's my profile at? I really don't like this website. Okay, it shows me as live, and when I click on it, it is coming through, I think. Yeah. So, I don't know. Do not know why it doesn't show when I'm logged out. Generally allowed to watch public live broadcasts. X-Zone page status states that public live broadcasts can be viewed on the web and embedded externally, not just by logged in users. Why is it when I visit my x.com profile page from incognito that it doesn't show the broadcast? I don't know, X just does a lot of weird shit. I don't understand it. You figured it would be pretty streamlined now. It's been a couple years since the acquisition and the rebranding and everything, but okay, so direct live URL should work, and slash media, maybe. Go to media here. That requires you to log in. Guess I slash live. No. What's the actual URL for this thing? Let's see. X.com. Oops. What did I say? Broadcasts. Totally different URL. So if I go over here, it's called iBroadcasts. Yeah, something is I prefix broadcasts. Of course, that way to log in, and then 1 WX WJALD GNJQ. Okay. Okay. So it does allow you to go to the broadcast and view live, but it doesn't surface it on your profile anywhere to logged out users. So, and like, I don't know how you discover the stream. Like on Twitch, there's like categories. You can literally just like scroll through them, and you could see like, oh, you know, co-working. There's someone streaming here. Let me check them out. But on X, I don't see myself like growing any sort of followership on X, because there is high level of friction for users to get access to your content. It's kind of silly that they do all that stuff. But yeah, I'll keep on doing it just in case someone wants to follow me on X. Okay, so we left off yesterday. We finished the first part of this problem 2, and then there's an extra credit with the array sum serial. Let's go ahead and just implement that. Let's see why not. Yeah. I mean, it's only 1 point of extra credit, but I like getting a little bit more experience with these, even though they're like fake SIMD intrinsics. Kind of want to get a little bit more experience with it. So let's go down here. So implement your vectorized version of array sum serial. So this takes an array and n and just sums up all the values and returns that sum. Interesting. So you want to sum the vector width. So we need to look at our header over here. Intrinsic.h. Is there any type of sum? I know there's an add. That's if you want to add 2 vectors. There's no sum, is there? Let's go back to the prompt here. Your implementation may assume that vector width is a factor of the input array size n. Okay. Whereas the serial implementation runs of n time, your implementation should aim for a runtime of n divided by vector width plus vector width, or even n divided by vector width plus log 2 of vector width. We find h add and interleave operations useful. Okay. Thanks for the tip. H add. Oh, okay. Adds up adjacent pairs of elements. Interesting. Oh, I remember. This is the half add. Interesting. So we might do a strategy where we do hadd and then interleave and then repeat in some type of loop. Returns the sum of all elements in values. You can't assume n is a multiple vector width. You can assume the vector width is a power of 2. Okay. Yeah, that's a good assumption. And we'll just use assertions. It's going to be n mod vector width is equal to 0 and vector width mod 2 is also equal to 0. That's if it's divisible by 2, not that it's a power of 2. How do I check if something's a power of 2? I take a log of it. So what we're saying is we have vector width to the power of width is equal to 2 to the power of n, and we want to figure out if that's a true statement. If there is an n, that can make this true. So you can take a log of it. So log base 2, which is ln. ln is natural log. lg, ln. What's the base 2 logarithm? I forget. What is the shorthand for base 2 log? lg. So you got ln, lg, and log, which is base 10. So you just say here lg of w. Is equal to lg of to the power of n. So you log both sides. Is that what I do? I forget. Alright, let's think about this. Well, let's just bust out a calculator here. So if we take log base 2 of, say, like 1024, it should give us back 10. Oops. I don't know why that's 1024. But if we do, like, say, 1025 or something else, it's not a power of 2. It would be a non-integer number, basically. Yeah. So we say log of w is going to be integer number, whole number. I don't know how to do this in C. So we do standard log 2, and then we just do a floor. Okay, that works. So it's going to be vector width and we'll do our assert here. Okay, now if we make this and we run it, just do myXP, we got a segmentation failure. Well, that's fascinating. Is that because I don't have an import or something? This thing's doing pretty much nothing but an assert. Why did that thing freak out in core dump? It's alarming. Okay. Oh, I want to see my assertion fail. That's why I was doing this. So let me go over here. Change this to be like 5 or something. Just want to see that fail. Wait a minute. Make clean and make and my exp. Is this where it's like doing it because I'm passing it in as flags? Vim makefile. There we go. Yeah, that's why. Can I just say C flags is equal to that? Is that valid? Or C++ flags? No, it doesn't like that. Oh no, this is linker input file unused because linking not done. We'll just delete it like that. I think that's fine. So now we have 5, but our assertion failed, which is what we wanted. Oh, they already have a test for that. Okay. So I don't even need to do my assertion. Vim, sorry, jobs, foreground. So the vector width being a multiple, or sorry, n mod vector width for this problem. Okay. Let's just leave the assertions in here even though they're not really helpful because the testing code is already kind of like ensuring that those are the case. Alright, and then in here we're going to do add and interleave. So let's test that out on like 2 values. Do some test cases here. So 2 value, a 4 value, an 8 value. I think that should be enough. So 2 values, say we have like 1 and 3. 4 value, we'll have 1, 3, 2, 5. 8 value, we'll have that, and then 4, 6, 7, 8. There we go. So if we do the interleave on this and an add, so the add's gonna give us 4, 4, and then we can just return the 0th element, which is 4. This one will give us 4, 4, 7, 7. And then we need to do an interleave, which changes to 4, 7, 4, 7. And then up here, we're going to have to do the same thing here, but with the 8, this will be 10, 10, and 15, 15. 10, 15, 10, 15. So we have to do another add here, which will give us 11, 11, 11, 11, and then we get out 11 here. Okay, and then down here, so we did our add, interleave, I think 7. I think the other 7 would go over here, right? Like up here, this interleave, I think it goes 4, 4, 7, 7. But I think over here, we get 4, 4. And then this is going to be 7, 7 like this. And then this becomes 10, 10, 15, 15. Okay, then we do an H add on that. So we're going to get 14 out of here. 14 out of here. 14 out of here. 14 out of here. And this will be 15, 7 would be 22. 22, 22, 22. Then we're going to have to do another interleave. So it'd be 14, 22, 14, 22, 14, 22, 14, 22. And then finally we do another H add, which would give us the sum here, which would be 36. 36. And I'm just gonna paste these in here like this. Boom, boom, oops. There we go. Okay, so it's a, so this is the original, and then we do a H add, and we're done. This we're do an H add, and then we have to do an interleave, and then an H add, and we're done. Okay, this is H add, interleave, H add, interleave, H add, and then we're done. 36. And just to validate this over here, I'm just going to do 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. EXPR, bing bing. Can I do that? No. Python. I think they have to have spaces in them for you to do that. That's 36. Cool. So taking the vector width and and log 2ing it like this gives you the exponent. And I actually don't like that it did that. We can reuse that exponent. So here, basically that exponent, in this case, 2 to the power of 1. exp is going to be 1. Oops. Two to the power of 1 is 2. Down here, the exponent is going to be 2. 2 squared. There's going to be 2 to the third. And you can notice you got exponent 2 here, you have 2 h's. Exponent 1 here, you have 1 h. Exponent 3 here, you have 3 h's. So our iteration here is going to be for I is less, and then I is less than exponent. We want to start at a 1 exponent, right? I guess it doesn't matter if we start at 1. Yeah, that's fine. And then this would be I plus plus. But we have to load. Yeah. I think what I'll do is undo this. This will be a J. So I think I have to load in. So load vect to sum. And then this is actually going to do the work to sum the vector into the last element and then return first element. It doesn't matter which element. They're all going to be the same at the end. Return a element. Or we say add a element to the accumulator, and we're guaranteed to have a 0th element, so we say what do we want to do? So we did our summing, and now we just say what, like we have our float accumulator is equal to 0 f, and we just say auto here, auto about digit f 0 point f. I think I can just say 0 point. Oh no, I'd say f to get the float instead of doing a double. Alright, then we go over n, and we're adding vector width each time. So now we have to do a load, which I did up here already. Where's the load? This load float thing here. Yeah, just copy that code. So we create our vec, we'll just call it a vec. And we're going to say, hey, you're going to point at the values plus I times vector width. And we're going to need the all ones mask again. So I'll pull that down here. Okay, so everything's loaded into vec. And then we're going to do vec. Sorry, this is going to be CS149. What is this? H add? Is that the thing? Half add between the two vectors. Oh. You have a source and destination vector? Interesting. We'll use the same vector for both. Why not? It should be vec and vec. So that takes care of the H add. I guess interleaving it initially doesn't matter. So if you do an initial interleave, that wouldn't matter. But we don't have to do that. I guess the other way of doing it would be to do the interleave the way I have it in the comment here. In which case you do the half add interleave. The interleave is redundant. So an interleave at the end here is kind of like not necessary. So we can knock that out by saying like if if j is equal to exponent minus 1, sorry, I'm like, this is not equal anyways. Okay. Then we do our interleave, which will be CS 149 interleave float. It'll be the vec. Okay. So assuming it's not the last iteration, then we're going to interleave. So that just saves, this is a minor optimization to save us a final interleave. But the algorithm's still correct if you do the final. So that's just a tiny optimization. And down here, of course, we're going to return the accumulator. And then here we need to store accumulator plus equals vec dot value sub 0, I think it is. Yeah. Make, or let me just do this thing here. Okay, expected 14.6 got 41.7 failed. Okay. Well, we'll have to debug this one. Just do some printfs here. So printf adding %d, or this would be f, and that's going to be vec value sub 0, and then we're just going to do a print vec maybe. Does vec have a length to it somewhere? Its vector width is always going to be the length. Okay, that makes sense. So we'll just say up here, void print vec, taking the vec, which is a CS 149 vec float, and we'll take it as a reference, and in here, oops, here, say for int I is equal to 0, I is less than vector width, I plus plus, and then here we're going to say printf out, and then we'll do a puts at the end to get the new line. But we're going to printf out here. What would this be? X? Let's say D. F, sorry, F. Put a space there. And then here is going to be vec dot value sub I. Okay, so that'll allow us to print the vec. So here we're going to say, hey, print vec and then printf entering some loop, and then we'll print the vec after the float. So after the float add, so this will be after add, hadd, should say. And then I'm gonna need some new lines here. Otherwise that's gonna get really messed up. And then this will be, we need to expand this to be a curly brace. And we'll say after interleave. Okay. So make, let's do that. So So we got all these. So basically, we want to end up adding the sum of these. Just go over here, Python, and we're just going to sum these together. Oops. Okay, so that's 7,4. So we got 7,4 on these two here. These didn't get added. But we did get the right answer because... well, these did get added together. Yeah, okay. We didn't do an interleave at the end. So this is our initial thing. So after the initial H add, we got 4422, which is correct. And then after the interleave, we got 42. This should be a 4, right? I don't see why that should be a 2. That seems wrong to me. So we need to go into the interleave float. So 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4. Okay, so it's a different type of interleave. I thought it was going to be different. Okay, so we got to fix our algorithm here. So the HAD comes up with that. This would end up being, that'll be correct because that's the way it is. This one's going to be different though. So we're going to do a half add, and then when we do our interleave, because this is, well, this is still width 4. So 0, 1 goes to the midpoint. And then the midpoint here comes back there. So I think CPP here, interleave. So this is saying, I remember reading this earlier yesterday, but this is saying that if I is less than half of the midpoint, basically, so if I is in the first half, then the index that we're going to write I to is going to be, oh no, the index we're going to read. Oh. So we're going to read from, I hate the way this is like written. So if it's the first half, we're just going to read from 2i. So if my value is 0, I'm going to read from 0. My value is 1, I'm going to read from 2. Oh, it's because it's being mutated as it's being iterated over. Yeah, it's no bueno. So the interleave, the HAdd is fine because the HAdd, if we look at that, which is this guy here, the vec result, we do our reads first and then we do our assignments. So that's safe. But the interleave here, we need two different things that you balance between. It's kind of weird that you can't do an in-place interleave. So we could have two different things that we balance in between. Or we could always read and write from the same one, but then do a swap. I kind of like the swap idea better. Okay, so we'll say vec1 and vec2. Can I just do comma vec2? Vec, and then we'll do current. So auto current is equal to vec1 reference. It's a pointer to vec1. I think pointers are fine though. Say cur dereference, and then this is going to be cur. I don't understand references in C++, so I'm just gonna from current to next. Next is going to be vec2. So we load into current, print out current. Here we say, hey, hadd float, which can just be current for both. And then we print out our current. And then here we say, hey, j, then we're going to interleave between current and next. And then down here we need to swap between the two. And then print out current. Swap. So we need an auto temp, which is equal to current. And then current is now equal to next. And next is equal to current. Sorry, next is equal to temp. So you need the temporary, I guess you can do XOR stuff to reduce that, but I don't care. Then down here it's going to be current value and current. Oh, we can do it like this. Boom, boom. Oops. There we go. Make, or do our routine again. It failed, okay. So we did our add after the interleave 4242. The interleave is correct. And then we do our hadd, and then we add our 48. Yeah. And then we do our read again of the next values. We get 1, 4, and 1, 5 is going to be 3, 97, and 1 is 1. We do our interleave. Looks correct. And then we got zeros here, which are fine, I guess. It looks a little weird to have zeros there. And then we add 0. And then last one we have this. So we did 1, 2, 3 sets because it's 12. But here we do our add, that looks correct, that looks correct. The interleaving looks correct. The add looks correct. Then we add. But expected 14. What would be 14? It would be 7 here. And 4, no. I think these numbers are like not correct. So what I'm going to do is at the top of the thing here, just as a debug thing, I'm going to say for int I is equal to 0, I is less than n, I plus plus, and then in here I'm gonna say, hey, print f out the value percent f of, and you know, I'm gonna put the plus sign there as well. And I'll put in here, this will be values sub I, and then puts. Get our new line. All right, and then so the pointer swapping here is all working, the interleaving's working, but something's wrong with the result. So I need to look to see what the result should be and validate it. So let's go ahead and do our make again. So now we get this huge string here, and what's nice about this is I can copy it, paste it over here. Yep, 14.6 is correct. So what happened here? Well, we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, these are negative values. 10, 11, 12, 13, 14, 15, 16. And we got zeros here. So these numbers aren't mapping evenly onto here for some reason. So let's look at our values. These look correct, the initial ones. So the next one's 0, 1, 1, 1. Which is not what we read. We read this stuff, which is 145. Do we see 145 anywhere? No. So something went awry here when we went to the next iteration. So something's wrong in our logic here. We're adding the vector width each time. So we're saying I is equal to 0, I is less than n. Oh. And then we I vector width. That should work. Let's validate I. Printf. And I'm just going to say, give a bunch of i's here. %d, new line, because I think I might be wrong. Let's do that. Okay, so I 0, 4, no, that's right, 8, 12. And then we got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2, 3, yeah. So the I is correct. Oh, so this thing maybe? Because it's I times vector width. We just want values plus I. Yeah, that was the load was incorrect there. Okay, so that should fix that. Let's go ahead and do that again. Hey, pass, cool. Before we delete all our print f stuff, let's do maybe like a different width here. So let's go back to the header file here, go up to the top, and we'll change this to 8. Or make, sorry, not make, make clean, all that stuff for passing. Let's go back over to here. Where's the write up at? Oh, this guy here. Your implementation should aim for a runtime of n divided by vector width plus vector width. Or even n divided by vector width plus log 2 vector width. Okay, did we achieve that? Let's get our printfs out of here. So that stuff can go. I don't need to print my vec anymore. Print. This stuff can go. This stuff can go. This stuff can go. So any other printing? Print is that guy. run it. Okay, it passes, but like he's talking about runtime complexity. Yeah, I don't know about this. N divided by vector width plus vector width. I don't know, man. I can't. It says your implementation should aim for the runtime of that, and I don't think my implementation achieves that because of the inner loop, where we're doing it's a log n on the inner loop. So it'd be n divided by vector width times log 2 of vector width. Not plus. So maybe that's a typo on their end, but I'm going to take another look at it to see if I can get it down to be less than that. But yeah, I'm going to take a quick break here. I'll be right back. Yeah, I mean, I'm leaning towards this being a typo on their end. But let's take a look at this. So our solution. So this main loop is going to be the n divided by vector width. Because we have to visit every block. We have to then do the sum on all the elements of the block. What's funny is if this was times, if it's n divided by vector width times vector width, then it would just be n. So indeed, we do want to get it to be plus. I mean, if we have times here, it is a bit of a benefit over O of n, because it's n divided by vector width times the log base 2 of vector width. And I don't know what that would evaluate to. Like, what is the log of x divided by x? Let's see if maybe Wolfram Alpha here. I'm not familiar with what this is mathematically. So ln of x divided by x. What does that evaluate to? Sorry, ln, or say log 2 of x. And is there a simplification? I don't think there is. If you look here, it looks very much like a log 2, though. So I think the log2 dominates, but I think you have to have the x in there because it's divided by x. It looks very, very flat there. So this is from 0 to 15. This is from 0 to 3. How is that even? So it goes up, goes flat there, and then it skyrockets and comes down. That doesn't make sense. Let's plot it on Desmos. Log base 2. How do I do that? How do I do a log base 2? Maybe here? No, those are just variables, functions. Okay. Just get a log. I just want a basic log. Those are trig functions. These are stats. List operations. Come on, there has to be a log. There's square root, there's a power. You telling me they don't got a log here? Here it is, ln. Bam. We'll delete that. It'll be ln of x divided by x. Okay. And if we look here, oh, this is where they compress one dimension and they expand the other to get that peak. I could see that. So this is a little bit more even between the two. But what they do here is they say this is like normal and this is highly zoomed in. The y-axis is highly zoomed in. So they're saying zoom out to 20 and then highly zoom in the y-axis and you'll see this peak here and then a gradual decline. Which is actually a really nice property. So our thing would be, instead of that, we're going to have 2 input variables. So I need to go into 3D. Let's do it here. Desmos 3D. Leave over here. And we're going to have y as well. So it's going to be y times log base 2. Y times all that divided by x. And I'll put parentheses around this to force the issue. Okay. Wow. I love these graphs that are like twisty. So x, y would be that. And then z pops out at you. So, oh, no, I wanted z here. Z times, okay, they don't let you do that. You have to do y. So that means that this would be, nope. This would be the plane that we're looking at. And we'll just say y is equal to what, 1? Yeah, so that's our original plot there, I believe. Was 0? Can't be 0. It has to be 1. Yeah, because it's multiplication. So that was our original plot. And can we give a slider for y and see how it changes? Is that something I can add manually? Maybe if I do like a Q here, then I add a slider Q. Okay. Q times guess I should have done that over here. On the other, what am I doing? Get out of here. Desmos. And this can be slided here. Okay. All right, I'm done looking at the plot there. So he's saying you should be able to get down to, at the very least, n divided by vector width plus vector width, or log 2 of vector width. Which means that this would have to be outside of this iteration. Which I can't see it working that way. So we load the vector in. We have to pay the cost. Because there is no O of 1 sum. If there is an O of 1 or even an O of n sum on the vector width, then we could do this. Let me think about it a little bit more. So we load it in. We do our half add. We interleave. We do a half add. I don't know of any other way of doing it, to be honest. I say stuff like that and then I think about it for a little while and then I figure it out usually. So when I say something like that, I'm not like admitting defeat. I'm just like giving my brain a challenge. So I currently do not know of any way of doing this that doesn't involve doing the log n operations. So what would it take to get down to what they're suggesting here, which is vector width plus a vector width? Let's actually plot this. So we have n divided by width plus width. So you have two variables. Let's use x to drive that. And then of course this needs to go out here, plus w. And we'll add a slider for that. Okay. So the vector width is normally going to be like a 4. Oh. Let me just do 4 here. There we go. So it's basically linear. I think you say O of n here. That simplifies the O of n. I guess what they're trying to say is like you're getting a better slope to this than if you just had O of n. And the more your vector width increases, the better slope you're able to obtain. So your vector width is 1, then it's going to be the same slope but offset because of additional w here. So what I was able to obtain from my thing was x divided by width times, so this would be x times the ln, which I need to go here, and then functions and all the bottom, was it? I forget where I found it now. All right, statistics. Here it is, calculus ln of x. Which, like, that doesn't seem right. Oh no, the multiplication has, no. Not ln of x, ln of w. There we go. So let me add another one here. Can I insert here? Add here? No. Add. Can I move these around? Yeah. Okay, so I'm gonna do one here, which is his other one, which is plus ln of w. So these are the two that he was suggesting, targeting, which are here. N divided by vector width, so it'd be x divided by vector width. Oh, maybe his precedence, he's saying, no, maybe, no, okay. N divided by vector width plus vector width. N divided by vector width plus vector width. Or N divided by vector width plus log 2 of vector width. So these are his two suggestions with, we'll say, vector width of 4. Oh, interesting. As width grows, the slope gets better on. So 4, we'll say 4 here. Yeah, mine's not as good when the vector width is 4. That makes sense. All right, so then we got what I have, which is x divided by vector width times. I'm gonna pull this out. Just, I mean, it doesn't matter that it's pulled out, but just to keep it like similar. Pull this one up to here, pull it down. Okay. Okay. And then if I go up to 8 here, it's going to be even worse. Can I do 16 here? So it's definitely better than linear. If we go back to the code, so this is n basically divided by vector width here, because we're adding vector width each time. And then when you go into the body of a for loop, you're usually multiplying. This is a constant based on this expression up here. Constant for the invocation of the main function here, the array sum vector function. It doesn't change, it's not a variable. In fact, I can probably do like const here, right? Const. Yeah. Oh, maybe because this is a const based on the vector width, not n. Maybe. But it still is going to be. No. It's a const based on the vector width, but we have a slider for that parameter down here. So you can't O of 1 it because it is dependent on W, and W is a variable in our analysis here. I was gonna say, like, if this is like always 3 for the invocation, it's like, okay, well, that's an O of 1 basically. So you can kind of sweep it under the floor, under the rug, but you can't because vector width is technically a parameter to this whole thing. It's vector width is not always going to be the same value, at least in our analysis, and that means that this exponent can change. It's always pretty small. It's log n. It's a small value. But every vector width. Oh, but it's. Oh, my math is wrong here. No, my math is right. We take x divided by vector width. Each one of those invocations, we do a log n of w operations. Yeah. So how would I get down to one of these? A plus W? Or, I think it's a typo on their end. I'll put that in the write-up. This will give me an opportunity to write some LaTeX. Because I'm going to have ChatGPT write it for me because I don't know how to do it. Write me some LaTeX for this. Oh, it's already LaTeX in. Okay. That means I can go over to here. Yeah. And go to my write-up. No, I have to edit. Write-up. There we go. And we'll just say extra credit. And we'll do boom, boom, boom. And then this will be in some type of quotes here. And if I go to the original Hugo theme, no style, please, I think it's called. Yeah. And then we go to our layouts. I think it was under, no, content, posts, and then tech here. And we'll do raw. So we have to say tech like that. Okay. Because if I just do this, it will show up. Can I say LaTeX or tech? Oops. I doubt that's gonna like show up correctly. Yeah. Yeah. Okay. So in here, we have to say mathjax is equal to true. This is not a blog post. So I can't use this. Never mind. I guess I could like pull it in as like a script tag, right? But let's see how GitHub does it. GitHub Markdown rendering LaTeX. You say $, $. $, left, and then $, $. Okay. Let's try that. So it'd be like this. And then the that render correctly? No. MathJax, open source JavaScript display engine. Issues, discussion, pull requests, wikis, and markdown. Okay. So I wonder why this isn't rendering here. Let's go back over here. Huh. How do I render this LaTeX on GitHub Markdown? God damn it. I hate it when I accidentally hit enter. Alright. It's a single dollar? Or I can do $$ as a block. $, $. Does not show up correctly. Okay, great. Let's see if this shows up if I go over here, do gist.github.com, paste it here and say foobar.md, and then I'll create a secret gist. It does show up correctly. Okay. I am using the tool grep, Python tool, to render GitHub Markdown locally, but it appears to not be able to do MathJax to render the LaTeX. What gives? Can I get it to do that? Math with a block is the newer GitHub supported syntax, but grep may still not render it locally. Grep run with user style script. That's if I want to do something like that. Okay. Let's go over here. Let's try the math thing. I actually like that better than this $$ thing. Well, it comes through as code. Let's check. I'm going to change some of these things. So this is going to be n divided by vector width dot ln vector width, like that. Let's copy that, and we're going to go to our gist again. I'm just going to close out of this. I don't think I need it anymore. This guy I'll close out of, and then we'll go do another gist. Boom, test.md. Vector width, like that. Okay. Desmos. Can I do ln of vector width? See, when you do the underscore, it like, how do I escape underscore in LaTeX? Just like normal escape, okay. Boop. Okay. Then we're gonna go over to here and wait a minute. Right up. What happened to it? Down here, we need to fix this to have that and that. So I was able to solve this using hadd and interleave. However, I wasn't able to get down to the runtime suggested. Oops. So their suggestion was n divided instead of a dot. Can I just do a plus here? What is the add sign in LaTeX? Okay, cool. Let's render that out as well. Just make sure that that comes through. Just does not like that with the C. So I think you just do like that. No. Huh. Can I do it like that? Yeah, it looks like that works. Okay. Maybe it's C dot and not C. That's probably what it is. Sorry, C dot and not dot, I should say. Alright, suggested instead my runtime was I can only assume this was a typo, but after thinking about it for too long, I wasn't able to get the runtime below this. Still an improvement from 11. Okay, cool. Status get at all, get DC. And I'm going to set my vector width back to 4. Should be .h here. Where is it? Oh, it's up here. 4. Okay. So you remove the flags, explicit flags from the makefile. We implement our vector sum, and we just had some text there to kind of explain what we're doing, and then our little write-up. Do you see anything wrong with this write-up? Maybe I'll copy it like this. Oh, annoying. Oh, that gives us the, yeah, that's not a, okay. Let's put that here. Bam. Asymptotic notation is inconsistent at the end. Yeah, I never said it wasn't linear. I guess I should say it's a constant factor improvement. The typo claim is probably too strong. Intended complexity may have been counting on horizontal reduction tree. On the horizontal reduction tree separately? A tree reduction over vector width lanes does take log 2 of vector width stages. Okay. Let's see if AI could just solve this then, because I'm giving up on it. I've done as much as I want to on this. Main dot cpp for prog2. And here say, can you get the asymptotic complexity down to the suggestion? Oh, Karen was very close, but the extra multiplicative log factor comes from the subtle but important issue in how the reduction is structured. Where your code is doing right now, you load vector with elements, then you do a reduction like this. Key point, each iteration is doing full vector-wide transformation, not shrinking the problem size cleanly in a tree reduction sense. So you're effectively doing log n vector width, full width vector operations. Each operation still consists of O of vector width work internally conceptually, as it leads to extra factor in your mental model. Why the target complexity is different, the intended optimization assumes each empty chunk is reduced using a tree reduction. Each stage halves the active lanes. So the cost per chunk is log vector width. And across the whole array, so total, not incorrect logically, but suboptimal in how reduction is staged. Repeatedly doing full vector shuffle, full vector HAD, instead of narrowing active lanes each step. That introduces unnecessary work per stage. How to fix it conceptually. You want load. Before I read that, let me think about it a little bit more. Okay. I give up. So load vector, replace in place like a binary tree. Reduce pairs, reduce halves. Final scalar. Each step should eliminate half the active lanes. That's what I do already, idiot. Key takeaway, your implementation, extra multiplicative log factor because each reduction step is full cost. Optimal SIMD reduction, active log factor, true tree reduction. Write the code for me for your solution. Because I don't understand even at this point what he's talking about. Okay, so we say for this for loop is still the same. We load in our values. And then here we take vector width divided by 2. So this is, say it's 16. Now we go to 8. Offset is 8. If offset is greater than 0, so not equal to 0 basically, then we do our thing. So we're at 8. We're at 8 here, and offset is not being used in the body of the loop. We then have a shuffled vector. We interleave everything, which is like an unnecessary interleave, and then we do the HAB. Yeah, this is the same thing. I'll just say your code is the same exact complexity of mine. I iterate on ln of vector width. Inside the SIMD loop after loading, and divide by 2 each time in your loop effectively does the same exact thing. Okay, moving on. I'll just add this to my write-up. How come I can't get the write-up? My fuzzy finder. It's weird. Write-up down here. Still a constant factor improvement from O of n. GW. I can only assume this is a typo, but after thinking about it for far too long, I wasn't able to. Still, my solution is a constant factor improvement of O of n, and ultimately, this is a decent constant factor. Oh, then I consulted AI on this problem after thinking about it, and it confirmed my suspicion about not being able to reduce the runtime lower. It may be possible, but I don't see it. Okay. Boom, boom. Problem 3. All right, next problem. Actually, you know what? I'm going to delete this. Save that. Get status. Get add all. Get status, get DC. Let's go and do our commit. So get LGA. We'll say get CI. Complete problem 2 extra credits. Now foregrounds, and here problem 3. This will be our actual ISPC program. So parallel fractal generation using ISPC. Is this Mandelbrot still? Now that you're comfortable with SIMD execution, we'll return to parallel Mandelbrot fractal generation. Like in program 1, program 3 computes a Mandelbrot fractal image, but achieves even greater speedups by utilizing both the CPU's 4 cores and the SIMD execution units within each core. So it's just using ISPC, so you don't have to write intrinsics. It's a compiler that it's like, okay, I can do this. I wonder if it'll work on my AVX 512 AMD CPU, since it's an Intel compiler. I guess so. They're supposed to be compatible, right? I guess we'll find out. I think Intel does things where it like biases its own chip, biases being more performant on its own chips. I think I heard them do that before. All right, program 3 computes a utilizing both the CPU 4 cores and the SIMD execution units within each core. In program 1, you parallelize image generation by creating one thread for each processing core in the system. Then you assign parts of the computation to each of these concurrently executing threads. Since threads were one-to-one with processing cores in program 1, you effectively assign work explicitly to cores instead of specifying a specific mapping of computations to concurrently executing threads. Program 3 uses the ISPC language constructs to describe independent computations. These computations may be executed in parallel without violating program correctness, and indeed they will. In the case of the Mandelbrot image, computing the value of each pixel is an independent computation. With this information, the ISPC compiler and runtime system take on the responsibility of generating a program that utilizes, sorry, my mind's wandering. I was thinking about the Mojo release. Someone sent me the Mojo language release. That's the initial release, but I heard recently there was like a May. Didn't make news, but if we go here, I think it was like a 1.0 beta or something. First half of 2026, yeah. Mojo language. Write like Python, run like C++, write fast code for diverse hardware using from CPUs to GPUs without vendor lock-in. A language that both user-friendly and memory safe. That's interesting. I wasn't aware of their memory safety stuff. The thing is, like, most people don't even consider, like, when they think algorithmically, they're not thinking in tensors or vectors or anything. So I think most people, there's still barrier to entry to GP program even on Mojo. It's not like it's like takes your Python code and magically executes it at the speed of C++. It's like, no, it's like a language that's like Python. It's not even Python. It's a language that's like Python that has interop with Python, that has types, and like this is a type here, type annotation. I guess it is kind of like doing global IDX.x, that's like in CUDA, where you get the global IDX. If I is less than layout size, then we say, hey, just do that. That's a bizarre way of like expressing that, to be honest. Because what you want to do is express, I mean, it's effectively, I don't know, it seems strange. Because it seems like they want to hide complexity, but it's not at the point where it's like, here's how you element wise add two tensors. Like this statement here and this statement here, I guess that makes sense. It says given an element, if that element is a member of the layout, which I don't know what layout is, it's not defined here, then add that index element from A, add that to B, and return or assign it into result sub I. So I guess it kind of is that. I guess, I don't know. This line here is a little bit like kind of weird to me. And this is kind of like, I think this is from like CUDA. Like CUDA kernels have this concept of like indexes like this. So I don't know. I have to play around with it more, but I'm not going to get around to doing Mojo until after I read a couple of books on parallel programming. SIMD vectorized kernel squaring array elements in place. So this is up here. Mojo makes GPU programming accessible to everyone without vendor-specific libraries and without separately compiled code. You can finally write high-performance GPU kernels in the same language used for CPUs. But the CUDA stuff is kind of bleeding through here. That's a vibe I'm getting from that. Python interop. Mojo natively interops with Python, so you can eliminate performance bottlenecks in existing code without rewriting everything. You can start with one function and scale up as needed to move performance critical code into Mojo. Your Mojo code imports naturally into Python and packages together for distribution. Likewise, you can import libraries from the Python ecosystem into your Mojo code. That's pretty sweet interop. I didn't know that you could create Mojo code that imports into Python. So SIMD vectorized kernel squaring array elements in place. Oh, and they have a comp time keyword. Kind of like Zig. What is this vectorized thing? Vectorized SIMD width. SIMD width of. Yeah, I gotta get more familiar with this language. Compile time metaprogramming. That's cool. And then they said something about safety. So I like that they're doing comp time like Zig. I love the Python interrupt. That's great. The SIMD stuff, the GPU, this is all great. This is like really great stuff. Quick start, releases, roadmap, contribute. It says explore Mojo on GitHub, but I don't think they're a open source project, so to speak. I think this is just their docs, right? The modular platform includes Max and Mojo. Yeah, not having Mojo as like a open source project that's separate from their corporate interests here, I think is going to hamstring it a little bit. in adoption because people just get like an ick feeling from it. Um, maybe I'm off on that, but that seems to be. I mean, it's kind of similar why like Swift, which is Latner's previous language. I don't want to fully attribute to this, but like it was kind of pigeonholed as a Apple language. I mean, it was backed by Apple, but then you look at something like Go at Google, and while Go is definitely sponsored by Google, and the Go team works at Google, I think most people who use Go view it as an open source project first and foremost because it was incepted that way. Like Rob Pike, Ken Thompson, and Robert Griesemer, from what I understand early on in the development of the language, set out to carve it out as a special open source project that wasn't tied to the corporate entity. Whereas Swift, it felt like it was very much Apple's language. Yeah, I mean, it was just like very much tied to Apple. Even though like I think technically it was a separate open source project, it kind of got that taint on it, which meant that like if you're doing Apple stuff, then great, you're gonna use it. But if you're not doing Apple stuff, you're not gonna use it. And I think they had a push to get it adopted with like server backend server programming, but I don't think that got super far. I might be mistaken on that, but that was my kind of impression. So Mojo being tied so much to their like corporate products, I worry that that's going to pigeonhole it to be like, oh, that's the language you use if you're a Mojo or if you're a modular customer. Not this is the language that you use because it's freaking awesome for parallel computing. I want to learn more about their safety. Safe. Modern Mojo draws inspiration from the best parts of modern languages like Python's intuitive syntax, Rust's memory safety, and Zig's powerful and intuitive compile time metaprogramming. Okay. Compile time megaprogramming ensure memory safety with compile time evaluation. Mojo's metaprogram uses the same language as the runtime code, providing an intuitive system to maximize performance. You can build hardware-specific optimizations with conditional compilation, ensure memory safety with compile time evaluation, eliminate costly runtime branches, and more, all with clearly defined intentions and zero-cost abstraction. Expanding Mojo to support more application-level programming. So this is phase 0 is complete. In progress is phase 1. With a guaranteed memory safety model and more abstraction features that developers expect for systems programming. Open source. Mojo's standard library is fully open source on GitHub, and we welcome contributions. We also plan to open source the Mojo compiler. Okay, so they're open sourcing it for 1.0. That's going to be big. We're committed to open sourcing all of Mojo, but the language is still very young, and we believe a tight-knit group of engineers with a common vision moves faster than a community-driven effort. If you'd like to get involved, join our developer community. Getting started installed. I think this might be the language that I learn next. I've been bouncing around. I spent probably like a couple months in 2025 learning Rust better, reading the Rust programming language book. I left that experience just like not happy. It's like a lot, that language. Compile times are high. They force tooling on you that is very opinionated, which has some benefits, but also like
I don't mind opinions as long as I can like easily do what I actually want to do, like break your opinions and go my own way. I need escape hatches. So put your opinions into your software. Like opinions should be defaults to guide users into a way that they should be going. But allow users to override those defaults. And I felt like Rust and Cargo and like all these other tools in the Rust ecosystem kind of like they're not designed in that way. And I think that comes from the Ruby community, because the Ruby community was very much like convention over configuration, where opinions are put into the system, and it's like there's a lot of friction to override those opinions. At least that was my kind of vibe of what was going on there. So Ruby Rust wasn't really like a fun language. Not to mention the borrow checker and the language itself is just like with their generics. I mean, it's amazing the technology that they put into that compiler and the development of that language, the language features. But yeah, it's like it makes me feel dumb. Like some of the stuff, I'm just like, the syntax. It's like it's hard to parse. It's foreign for me. I'm more of a C++, Go, Python, JavaScript. Like those languages feel very familiar, very comfortable to me. But a language like Rust, it seems like it's more inspired by Haskell or Erlang. I think it came out of, no, it's not Erlang. What was it? OCaml. I've never done any OCaml. The compiler's book that I have is in OCaml, so I might be learning more OCaml. But suffice to say, it seems like it comes more from like a functional programming perspective. A lot of the language features, and then pointers and borrowing and mutation, especially when you're doing like multi-threaded concurrency, ownership, moving things around. I mean, I'm sure if once you get like 1,000 or 2,000 hours of experience dealing with that type of problem, the language is like great. I'm sure that's the case. Lifetimes, non-lexical lifetimes, the lifetime annotations, like a lot of that stuff, I just like, I felt like I gained some type of understanding of it. But if I sat down at like a blank Vim buffer and had to write some Rust code using lifetime annotations, other than like, I think static was one. Like static's like an obvious lifetime, so using that as like static just means that it never goes away because there is no memory management for it. Its lifetime is the lifetime of the process. But like using like the tick A and tick B for like parameterized variable lifetimes, and that's like apparently that's also part of the generic system. I just like at some point my brain was just like, this is so freaking complex. Like I think C++ templates are easier than this. Go's generics are way easier than this. And it's like, what am I getting out of this other than a bunch of frustration, confusion, and complexity? At least that was like my thought process when I was doing Rust. And the answer is like you get memory safety. You get compiled time memory safety. That's the trade-off. You deal with the borrow checker. You deal with these like weird freaking things, and this weird language is kind of weird when I think about it. But yeah, you deal with this like this weirdness, and you get memory safety as a result. Unless you use unsafe, which a lot of people, they're like, Rust is great if you just put it in an unsafe block. And it's like, well, that defeats the whole purpose. The main selling point of this language is that it's giving you a compiler that is so advanced that it can guarantee memory safety at compile time if you follow certain rules. And the main rule is you don't put your code in an unsafe block. So anyways, if modular can touch on memory safety in a way that is like even just like 1/10 of the memory safety that Rust provides, while still being like a fun programming language to use, then I think that's going to be a win. Because it just feels like a lot of people just don't like Rust. They don't like the experience of programming in Rust. I think on a dopamine level, I would say like Rust is probably the least fun programming language I've used. I think C++ I've had more fun with. I've had more suffering with as well. But like C++, I've had more fun programming than I have with Rust. So anyways, it's enough rambling here. I look forward to their releases. I think they're 1.0 beta 2. So the beta 1 was May 7th. So they just did a nightly release for their beta 2. Is this the compiler? No, that's a 404. Okay. Modular tree mojo. Okay. This isn't the compiler though. This is like docs, examples, integration tests, proposals, standard library. So I think they're going to be releasing the compiler, they say this year, but it makes sense to do it with the 1.0 push, right? Oh wow, they got a lot of contributors already. Cool. I'll check back in on them. But back to ISCP, or ISPC, actually. Intel SIMD Parallel Compiler. What does it stand for? ISPC stands for Intel Implicit SIMD Program Compiler. Implicit. I always thought it was Intel SIMD, but they're saying Intel Implicit SIMD program. Okay. What's funny is like at the bottom here, he talks about this Intel. Oh, sorry. The story of ISPC here, and I'm pretty sure I read a good part of these blog posts already. So I'm like wondering how much of this Git repo have I gone through already and done. All right. These computations may be executed in parallel without violating program correctness. Indeed, they will. In the case of a Mandelbrot image, computing the value of each pixel is an independent computation. With this information, the ISPC compiler and runtime system take on the responsibility of generating a program that utilizes the CPU's collection of parallel execution resources as effectively as possible. You will make a simple fix to program 3, which is written in a combination of C++ and ISPC. The error causes a performance problem, not a correctness one. With the correct fix, you should observe performance that is over 32 times greater than that of the original sequential Mandelbrot implementation from Mandelbrot serial. Okay. Program 3 Part 1, a few ISPC basics, 10 out of 20. When reading ISPC code, you must keep in mind that although the code appears much like C, C++ code, the ISPC execution model differs from that of standard C, C++. In contrast to C, multiple program instances of an ISPC program are always executed in parallel on the CPU's SIMD execution units. Oh, that's right. Now that I'm revisiting this in my mind, they, even though it's like one single invocation from like a Unix or Linux exec VE system call perspective, what they're saying is that like your entire program is effectively a parallel program. Like it is, and there's instances of it, and it's running in parallel. I forget what there's a terminology for that I've forgotten. It's single program multiple data instead of single instruction multiple data. So SPMD instead of SIMD, it's SPMD. Yeah, SPMD model. In contrast to C, multiple program instances of the ISPC program are always executing in parallel on the CPU SIMD execution units. It's an odd way of putting it. The number of program instances executed simultaneously is determined by the compiler and chosen specifically for the underlying machine. This number of concurrent instances is available to the ISPC program via the built-in variable program count. ISPC code can reference its own program instance identifier via the built-in program index. So this is very similar to like CUDA with its indexes. Thus, a call from C code to an ISPC function can be thought of as spawning a group of concurrent ISPC program instances referred to in the ISPC documentation as a gang. The gang of instances runs to completion, then control returns back to the calling C code. Stop. This is your friendly instructor. Please read the preceding paragraph again. Trust me. Okay, let's do it again. When reading ISPC code, you must keep in mind that although the code appears much like C, C++ code, the ISPC execution model differs from that of the standard C, C++. In contrast to C, multiple program instances, and these aren't processes in the Unix sense, these are just like logical program instances of an ISPC program are always executed in parallel on the CPU's SIMD execution units. It's a rather weird way of putting it, but I understand what they're getting at. The number of program instances executed simultaneously is determined by the compiler and chosen specifically for the underlying machine. This number of concurrent instances is available to the ISPC programmer via the built-in variable program count. ISPC code can reference its own program instance identifier via the built-in program index. Thus, a call from C code to an ISPC function can be thought of as spawning a group of concurrent ISPC program instances referred to in the ISPC documentation as a gang. Would this be a warp in CUDA terminology? I'm not sure. The gang of instances runs to completion, then control returns back to the calling C code. So basically, it's just SIMD the entire code without having to do intrinsics or auto vectorization on the compiler side. It's like, I'm going to take your C code, and literally every single statement is going to be a SIMD statement. As an example, the following program uses a combination of regular C code and ISPC code to add two 124 element vectors. As we discussed in class, since each instance in a gang is independent and performing the exact same program logic, execution can be accelerated via implementation using SIMD instructions. A simple ISPC program is given below. the following C code will call the following ISPC code. So this is a C code. We have a const int called total values, which determines the size of 3 float arrays. We introduce some initialization to set values, and then we sum. N is going to be total values, A, B, and C. So A is going to be the result, and B and C are the two things you're going to sum probably. Upon return from sum, results of A plus B are stored. Okay, so that's inverted from what you would assume. That's why, I don't know, I prefer the convention is the left-hand side is the thing that's getting written to. And these are operands for the operation. So it's right to left assignment, just like assignment is. And I think Intel syntax also for assembly also does right to left, like your register that you're writing to would be on the left-hand side. And then GNU AT&T assembly is left to right. And I guess this is just code that he wrote, so he chose left to right, which is an interesting choice. The corresponding ISPC code, so you literally call it .ispc to indicate that it's not regular C++ code. So you say export sum, and then, okay, this is totally different. Uniform int n, uniform float star A, uniform float star B, uniform float star C. I forget what uniform is. Uniform means that you can't alias the memory that's being pointed to, which would make sense for these, but why would uniform be here for n? I wonder if uniform is uniform. Is uniform a keyword in C++? Oops. If so, what does it do? So that's a ISPC concept. What is the keyword in C++ to ensure that aliasing doesn't happen? Restrict. You're promising the compiler during the lifetime of this pointer, it is only way to access the memory it points to. Which means that alias, so the compiler is allowed to assume that no aliasing through other pointers. Yeah, so it's restrict was the keyword I was thinking of. And you put it after the type. Interesting. All right. Assumption program count divides n evenly. So this is where we're iterating over the SIMD width, basically. So for I is equal to 0, I is less than n, I plus equals program count. Program index plus I. Oh, and this is because like I think what's happening here is like this is obviously being done on SIMD sized elements, right? Because they're plus equal. Oh, that's weird. Why would it be that way? You're selecting columns. So n is going to be the total values. When we plus equals program count, we go to the next column. We're adding together columns. That's weird. I wouldn't have written. I mean, I guess my mind is more used to the intrinsics style. Writing it this way seems weird because it looks like you're doing column access, like, and that usually is a bad idea because it's like you could potentially be accessing columns in different cache lines. The ISPC program above interleaves the processing of array elements among program instances. Note the similarity to program 1, where you statically assign parts of the image to threads. However, rather than thinking about how to divide work among program instances, that is, how work is mapped to execution units, it is often more convenient and more powerful to instead focus only on the partitioning of a problem. Oh, maybe what they're doing here is they're showing you the column, which is a slow way of doing it. And then they're going to show you, hey, just tell us which parts of the problem are independent using for each. And then that will fix the column access performance issue. To instead focus only on the partitioning of the problem into independent parts, ISPC for each construct provides a mechanism to express problem decomposition. Below the for each loop in the ISPC function, sum2 defines, what time is it? 5:07. I need to hop off here for dinner. Defines an iteration space where all iterations are independent and therefore can be carried out in any order. ISPC handles the assignment of loop iterations to concurrent program instances. The differences between sum and sum2 below is subtle, but very important. Sum is imperative. It describes how to map work to concurrent instances. The example below is declarative. It specifies only the set of work to be performed. I'm biased towards more imperative solutions for performance, because you have a declarative form, which is great for generality, but then when you want to optimize for a specific situation, you typically want to like make it very much imperative. Before proceeding, you are encouraged to familiarize yourself with ISPC language constructs by reading through the ISPC walkthrough available here. Okay, well, we'll do that after we get done with dinner. The example program in the walkthrough is almost exactly the same as program 3's implementation of Mandelbrot ISPC and Mandelbrot ISPC. In the assignment code, we have changed the bounds of the for each loop to yield a more straightforward implementation. What we need to do, compile and run the program Mandelbrot ISPC. The ISPC compiler is currently configured to emit 8 wide AVX2 vector instructions. We can do better than that with 512. So that'd be 16 wide. So AVX2 would be 256, right? Divided by 8. So 32-bit is the size of their type. So I should be able to do 16. So 32 bits times 16 should be 512, yeah. All right. And then what is the maximum speed up you expect given you know about what you know about these CPUs? Why might the number you observe be less than this ideal? Hint, consider the characteristics of the computation you're performing. Describe the parts of the image that present challenges for SIMD execution. Compare the performance of rendering the different views of the Mandelbrot set may help confirm your hypothesis. Remind you that the code described in this subsection, the ISPC compiler maps gangs of program instances to SIMD instructions executed on a single core. This parallelization scheme differs from that of program 1, where speedup was achieved by running threads on multiple cores. If you look into detailed technical material about the CPUs in the myth machines, you'll find there are a complicated set of rules about how many scalar and vector instructions can be run per clock. for the purpose of this assignment, you can assume that there are about as many 8-wide vector execution units as there are scalar execution units for floating point math. Okay, so I'm gonna take a break here, and then when I come back, I will read this and get started on the Mandelbrot problem after I read this. Cool. All right, I'll be on in probably about, let's see, it's 5, probably around 7. And I'll get maybe about an hour. And cool. All right, be on later. Bye.